Okay, doing the same demented problem, I'm going to start all over. Just give a quick explanation. Remember, 10% of your sane become demented, 20% of your demented become sane. You start with 1,000 sane, and you get this matrix. 90% of your sane and 20% of your demented will be sane in the next period. 10% of your sane and 80% of your demented will be demented the next time. So if we multiply this matrix by the vector that depicts the number of sane and demented, we get the new number of sane and demented. And we represent that by A, x naught equals x1 in this case. X naught is this, x1 is this, okay? Now, if we multiply the same matrix by x1, your 900, 100, comes out 830, 170. Now I got time out in the mental arithmetic here because I couldn't add 56 and 80, which is 136, not 126. Okay, got that fixed in my head. And then I forgot to do a couple of things here, so keep an eye on me. But if you multiply this matrix by this, well, 90% of 830 is 747, okay? And 20% of 170 is 34. We add all that up to get 781. 10% of 830 is 83. 80% of 170 is 136, not 126. And now these numbers add up to 1,000. Okay, I got hung up in the arithmetic, I'm sorry. Okay, so if we look at the number of sane, we get this simple sequence. Now you've done some stuff with sequences and series and calculus very recently, right? Okay, so I'm going to pull a little bit of that insight into this at a fairly simple level. Okay, we get 1,000, 900, 830, 781. Okay. The change in the number of sane is negative 100, negative 80, negative 70. Okay, that's what it ought to be, and negative 49. Okay, what do you note about these numbers? Well, it depends on how your mental arithmetic is, but 70% of 170, 70% of 70 is 49. Okay, this sequence continues. It's an exponential sequence. It's a power sequence. Well, use the term geometric sequence. Where every term is the same proportion of the previous one. Sequence would be like Sn equals 0.7 Sn minus 1. Okay. Now this sequence approaches 0 fairly rapidly. Okay, 70% of 49 is 35 minus 0.7, 34.3. Okay, so that in 1, 2, 3 steps, you're down to about 1/3. Okay, of the difference that you had. So the change in the number of sane becomes less and less. Okay, it decreases and approaches 0 pretty rapidly because after 3 transitions, again, you're down to about 1/3. So that means after 6 transitions, you'd be down to 1/3 of that, which would be 1/9, which is kind of around 1/10. So after 6 transitions, you're down to about 1/10. After 6 more, you'll be down to 1/10 of a tenth, which is 100th. Does that make sense? Does that fit in with some of the stuff you did in calculus? Okay. Now we can actually, use the 1/1 minus r thing to figure out what the sum of this sequence would be. So you figure out the total change in the number of sane. Okay. Forever. Well, we know from what we did back much earlier in the semester that in this case, and you might not remember, but in this case, the ratio of the number sane to demented, this approaches two-thirds of 1,000. Okay, and you can set up a simple equation. This matrix times an unknown vector equals that unknown vector. Okay, but what it comes down to is this matrix multiplied by, we'll say 2,000 over 3, 1,000 over 3, and of course 2,000 over 3 and 1,000 over 3 add up to 3,000 over 3, which is 1,000, equals this. Okay, and we get that by solving the equation AX equals X. Meaning that lambda equals 1 is an eigenvalue. Okay, now I'm going to let you ponder that for a second. Okay. And that's going to be a characteristic of any stochastic matrix. Haven't proven. We prove it for the 2x2 matrix. Okay. Proved it for 3x3 is a little more complicated. We're not going to get into that, but just kind of pose it the problem. So what I want you to do is for this matrix, find the eigenvalues in an eigenvector basis of A equals 0.9, 0.1, 0.2, 0.8. So while you're working that, I want to take a look at some of your written homework. And let's zoom the camera in just a little more. Yep, that does it. Okay, I wrote this down too quickly. The 0.2 goes here, the 0.1 goes here. So let's work that one out. Thanks for pointing that out early. Okay, working out the eigenvalues, we get the characteristic equation. It's very straightforward. I'm going to go through this detail of that. And I think I get this. Okay. And minus 4AC, so that should be plus 2.80, not minus 2.80. You agree? Got a comment here. I'm obviously doing something silly. Okay. Yeah, that should be plus 0.70, 0.9 times 0.8 minus 0.02. And that does make this negative, which makes me a lot happier. So thank you. So this is 0.09, and it's easy to get the square root of 0.09. It's 0.3, because the square root of 5.69. That's forgotten actually. Okay. So much happier now. So that's negative 1.7 plus or minus 0.3 over 2. And that's going to give you negative 0.7 or 1. So as we said, 1 clearly has to be an eigenvalue. So if you don't get 1 as an eigenvalue, like I wasn't gonna, I believed everything I did there. It's very easy to make a mistake and mess that up. So that's pretty straightforward, okay? Now the eigenvectors, LP season should be winding down any day now. Won't be too soon. Okay, eigenvectors. You would have the determinant of, okay, for lambda equals 1, you get determinant of 0.9 minus 1, 0.2, 1, 0.8 minus 1, which equals times we've already determined the determinant equals 0. We want the matrix. Multiplied by xy. Etc. Giving us the reduced, the augmented matrix, negative 0.1, 0.2, 1, negative 0.2. That should equal 0. And I'm using xy instead of x1, x2 because we want to bring this into the xy plane. That's kind of what we're used to seeing because we're going to graph these vectors, okay? So it's very quick without going through all the details to see that, set it right here. So let's write it up. Negative 0.1x plus 0.2y equals 0 because people are getting the wrong signs on this. Okay. I've seen a lot of vectors that have x and y with opposite signs, but when you solve this, you get 1/2 x. Okay. So typical eigenvector. The any vector for y is 1/2 x. So we can just have 1, 2, out and 2, 1. Sorry. And on a couple of papers, I saw 2, negative 2, 1, or 2, negative 1, or negative 0.2, something like that. Okay. But clearly it comes out like this. Okay. So all that v1 equals 2, 1. Now we're going to get to the graph. So here is B. Instead of writing it as a column, I'll write it in order pair notation, which we often use for graphing vectors in the plane. Okay. Your other eigenvalue is negative 0.7. Now, negative 0.7 is going to lead you to 1.6x1 plus 0.2 x, okay, we're using x and y. That's 0.2 y equals 0. Because if lambda is negative 0.7, 0.9, minus 0.7, 0.9, plus 0.7, that's 1.6. Just checking it out and make sure I'm doing it right, because that doesn't look good to me. But then you get 0.2 here, okay? So you get like 1.6, 0.2 down here, you get 0.1. 1.5. It's not negative 0.7, it's 0.7. Okay, okay, that's not working. These wouldn't be compatible. So again, I knew that wasn't looking right. So you get 0.2x plus 0.2y equals 0. So that x equals, or let's say y equals negative x, and v2 would be I could use 1, -1 or -1, 1. We're going to do -1, 1, which means we like here. Lambda 1 implies this, lambda 2 implies this. Okay. Now what this means is when you do the transition of any matrix or any vector, well, let's say we have the vector 1000, 0. And let's start with 0, 1000. I like that. Yeah. I'm going to have to take a few liberties with scale. Well, that doesn't represent 0, 1000 because these vectors are only a couple of units long. 1000 would be, higher than you want to fall from. Okay, it's pretty much an instant fatality. Okay, or quick fatality at least. That maybe not much about it. Anyhow, okay, what happens to this vector when you do the transition? Well, this vector is a multiple of this vector plus a multiple of this vector. Okay, so let's just say you express this in terms of your eigenvector basis. Okay, now, I know everybody knows how to do this, but not seeing a lot of good results. So what you got to do is you got to say, okay, got to find C1 and C2, set that these things add up. That's what it means to express the vector in terms of the eigenvector basis. So when you're doing the change of basis and all that stuff, well, that needs to be kind of a reflex. And of course, everybody is doing that. I've just looked at a little bit of your work, and people have done it with complex matrices, okay? But is it really sinking in what you're doing, okay? So make sure it is. And for the work I've seen, I think y'all are going to be fine with it, but there's one thing to kind of be aware of. Make that 1000 a little prettier. Okay, so real quickly get this, kind of make yourself a note that this is what it means to express a vector in terms of a basis. You got to solve the system of equations or matrix equation, whichever. Well, you write this equation. This means you have C1 times 2, 1. Let's see, 2 times negative 1, 1 equals 0,000, which gives you 2C1 minus C2, C1 plus C2 equals 0,000. Okay. And this tells you that C2 has to equal 2C1. Okay. And C1 plus C2 equals 1,000. Now, there are other ways you do this. You can easily reduce this matrix. Okay. Like if you added the two, add the first row to the second, it doesn't eliminate C1, but it eliminates C2, and you get 3C1, okay, equals 1,000, okay? So make sure you understand that. I don't have time to write that out because we want to go on and make some other connections. But again, as I've preached from the beginning, and as y'all have been very good with, pretty much any question comes down to a system of equations. And you can represent that system as a system. You can represent this as a matrix equation. You can do an augmented matrix. You do whatever. If you do the augmented matrix and add the first row to the second, you immediately get a solution, okay? For C1, which is 333, okay? Well, 1,000 over 3. So okay. Oh, on the picture. Now, what does that do? Well, that tells us. I'll do picture because I've got some board space. Keep running off with my chalk. How can I run off with my own stuff? Okay. So V1s are 2, 1 vector. You multiply that by C1, you have basically 1,000 over 3 times the 2, 1 vector, right? So here you have over 3 C1, and then here you have, so that's C1 is B1. And then you have 2,000 over 3 V2. So that's a bigger vector up here. I should have left myself a little more room. Okay. I have to redraw this. I don't have enough room to draw my original vector. Okay, so here is my (1,000 over 3 V1), and here, and note that this vector is not perpendicular to this one, which I knew before I drew it. Then I drew it to almost perpendicular. don't have control over my drawing. Okay. So let's say here is 2,000 over 3. V2. And when I add these two vectors, well, it's not drawn very well to scale. Could have been more careful. So here I have my original vector. Zero, 1,000. Okay. Now, if I apply my transformation, let me get this. The angles between these vectors are not right. When I drew it. This vector is like at 45 degrees. This vector is closer to the x-axis than it is to the y-axis. So this is really an obtuse angle, but it looks like a right angle the way I just drew it. Okay. Yeah, could have been more careful. Okay. In any case, what happens now when we apply the matrix? Okay. So let's take A times 1,000 over 3V1. What does that equal? Well, you could plug into the matrix, but we know that V1 is an eigenvector with eigenvalue 1. Okay. So this is, it's 1,000 over 3 times A V1, which just equals 1,000 over 3 times V1. In other words, this vector doesn't change because V1 is an eigenvalue with value 1. Okay. So can you tell me what happens to this vector? Okay, I think I've really either got it or on track. Let's be sure. Well, this is $2,000 over 3 times A V2. What's A times V2? 0.7 V2, because V2 is a vector, an eigenvector with eigenvalue 7. Okay. Meaning in the next transition, apply the A matrix. Sure. Things on the screen. Can't really see my screen very well from here. Okay. That my vector here is going to be the same. This vector isn't going to change because V1 is an eigenvector with eigenvalue 1. So this is still $1,000 over 3 V1. I've got these backwards. I'm not going to worry about it. process is clear whether I've got them backwards or not. Wouldn't be surprised. Now, this vector is going to shrink by a factor 70%. Okay, so this is my %70 of. Okay. Yeah, that works. So that when I add these vectors, no, it's not working again. Yeah, it is. Okay, I now get a vector that's turned toward this one. Okay, well, this is my vector. It was 900, 100. Should be. Yeah. That P2 is badly written. But it's this plus this, right? And that gives you 900, 100. And you can work that out. You can do 0.7 times 2,000 over 3 times -1, 1. And add that to 2,000 to 1,000 over 3 times leave 1, and you're going to get to 900, 100. Now, geometrically, what's happened is that the component of this vector in this direction never changes. The component of the vector in this direction always shrinks by 70%. Okay, so that in the next transition, I have to write a little smaller. We don't have enough board space, but you're again going to get over 3v1 over here. This vector is going to get even shorter, 70% as well. So this is .7 of this one, because this one always has to shrink by 70%, because V2 is an eigenvector with eigenvalue 0.7. So you get this, and now the vector is turned even more toward this vector. Well, I guess that's draw it particularly well. You get the idea. Okay. So you have this picture. Of this stable vector here. 1,000 over 3v1, which is (2,000 over 3, 1,000 over 3), because V1 is 2, 1, right? Which is and it's not an approximation because I've got the repeating. 666 and 2/3, 333 and 1/3. Then we have this vector. I've drawn a little more accurately. It's actually more famous than that. Okay, you've got this vector. Which is along the line of V2. In this case, it would look something like this. Now this vector is twice as long as this one, and I still don't have the picture right. But we get eventually I'm going to get a piece of chalk out of that tray and not lose it. There, I did it. Okay. So there's my eigenvector. There's my V2. Not drawn to scale because it's much, much shorter than these because these are hundreds of times longer. Here's my vector. (2000/3 V2), which maybe projects up here just a little more. But anyhow, that's going to be the same as this vector. And this is my initial vector. So centric triangle. Okay, now I need to get a big barrel full of colored chalk. So I never fail to find what I'm looking for. Okay. This vector, when you transform it, keeps getting shorter and shorter. This vector stays the same because they're eigenvectors with the eigenvalues 1 and 0.7. So this vector keeps shrinking. It goes down to 70%. So when I add 70% of this vector up here, I get this. Okay. Then it shrinks by another 70%. Well, it shrinks by 30%, shrinks to 70%. Okay. And it gives me the vector that is out here. Okay. And then it keeps happening. The transformation just keeps shrinking this vector down to 70% of its length. The vector stays on this line. So these vectors, you know, this vector here, if we add to this one that doesn't change, stays on the same line. And we just get a series of vectors that approach this vector as a limit. Okay. So that's a picture. It explains pretty much everything you see with this model. I'm going to ask you to do a problem for homework, just a single problem. Okay, same thing. Just do it with your A, B, and C values. Okay, so do it for the matrix. Should be able to write this out somewhere. Here. Alpha, 1 minus alpha, 1 minus beta, beta. We can see that this is a stochastic matrix because these numbers add up to 1. Both columns add up to 1. Where alpha is 1 minus C over 10 with your C value, and beta is 1 minus your G value over 10. So everybody will have slightly different numbers. And they probably won't work out quite as nicely as 0.1 and 0.2. You know, if alpha was 0.1 and beta was 0.2, or 0.9 and 0.2. Okay. Yeah, what we did, alpha was 0.9, beta was 0.2, right? And those numbers are nice and round. Your numbers are less round, so you can all use a little calculator, but the process is identical. And I'd like to see the entire picture with explanation. If you can do that, then you have command of probably at least 30% of the course. Okay, maybe more. Pull all that together, it pulls together just all kinds of stuff. Okay, so that's kind of neat. Well, there's another thing that I kind of wanted to do, but probably don't have time to do it. Just rotation matrices. The neat thing is, I'm going to actually do you've seen rotation matrices, you will see them in that section 7.4, I think. Or was it 7.4? Pretty much had to be 7.4 because it involved eigenvalues and stuff. Couldn't have been the first chapter. So, and if you've done that, you see that they give you these formulas for the discriminant of a quadratic form. Okay, if you haven't seen it, you'll see it. They don't explain why that formula comes about. So, but still, it's important to be able to apply it. But let me tell you a little bit about where the thing comes from. Okay. And just do what we can do in another 7 minutes. And we're still recording. I mean, recording that. The board is confused, or the camera's confused. Or we're back in focus. No, but there it goes. Okay. Just take a picture. Of a vector. Okay. Vectors. I'll just call it x, y. Since we're in 2 dimensions. Okay. Then I have a x prime, y prime axis out here. And I want to express, I want to change bases. So the x prime, y prime. Okay. Well, you have a mechanical procedure that you've learned that'll get that done. But we want to see it more geometrically. And I don't think your text does the details of the geometric connection. Now, maybe the easiest way, because I always had trouble seeing this when I first saw it. It's just some formulas and a picture that really, I guess it's the standard picture. So it's just my brain just didn't resonate with the explanation. I could always get the rotation matrix. I could do it, but I never, at least for a while, I didn't understand it very deeply. So let's go ahead and express this vector xy as x times your I vector and y times your j vector. Okay. Now, the I vector with respect to this rotated coordinate system, and the angle of rotation is going to be theta. So we have angle theta. Well, the I vector then has a component in the direction of x prime and a component in the direction of y prime. And before I go on, I'm going to make the vectors bigger so you can actually see what I'm doing. So here's x phi. So here and here are the components of xi in the direction of x prime and the direction of y prime. Okay. So let's draw those components. Here. Doesn't take a huge amount of insight to see that this component, well, this is the adjacent side of a triangle formed, right triangle formed here because the projection goes at a right angle. So that this vector is going to call it I prime equals I'm not going to call it anything. I'm just going to say it's x cosine theta times I prime. If this vector is xi, if this hypotenuse is x, this is the adjacent side, you multiply by the cosine, right? And down here you get negative x sine theta times j prime. Okay. Similarly, with green, I want green. I don't see green, I'll use some. Okay, then we have our y. Yj by similar projections. Yj is the sum of this component and this component. Now, I'm not going to try to write out the details, but clearly this has magnitude y, okay? And this angle here is theta. So this is y sine theta down here times the I prime and y cosine theta times the j prime. Color. So down here I can say that x I equals x cosine theta I prime minus x sine theta j prime. Well then, if I multiply xy by cosine theta negative sine theta, sine theta, I got that wrong, negative sine theta here, cosine theta, I get this vector, which is this vector according to the other. Oh, well. Yeah. I don't want to say all the words because I'll get them wrong. Okay. Okay, this is the reason you would multiply the components of this vector by this matrix to get the vector with respect to the other basis. Okay, so this times this vector in this basis equals this vector, which is the vector in the other basis. Okay, the inverse of this matrix is this, which you can see by multiplying this row by this column. You get cosine squared plus a sine squared. Multiply this row by this column, you get a sine squared plus a cosine squared. Okay, so first row times first column gives you 1. Second row times second column gives you 1. First row times second column gives you a negative cosine sine and a positive cosine sine, which is 0. So you can easily see just from the Pythagorean identity that these matrices are inverses. Okay, so one of these matrices is a rotation matrix from this basis to the rotated basis. Okay, and the other matrix takes you from the rotated basis to this basis. Whatever way this thing is explained, you probably haven't seen it explained this way. Okay, and this picture can help you understand the rotation. Now, rotation's a big deal. You combine rotations with expansions in different directions, which is what happens with eigenvectors, and you pretty much get any type of transformation. Well, almost any. Okay, so it's another important part of the picture for what's going on in the course. And unfortunately, I didn't have time to give you a detailed explanation. That should have been spread out for about 10 more minutes, okay? So I could make all the connections.